Chris is the co-founder of FortyNorth Security. He's also the current developer of the Veil framework, which aims to bridge the gap between advanced red team and penetration testing tools. He also developed the WMImplant, EyeWitness, and all kinds of other stuff. Definitely check out their GitHub. He's also the author of 3 different classes, the initial access ops, the intrusion ops, and the assume breach ops, which is coming up soon. So definitely check those out. And with that, I'll turn it over to you, Chris.
Thanks, Corey. Appreciate it. All right. Let's get started. So today I'm going to be talking about WhatTheF. Just as a heads up, Corey, I can't see Discord. So if any questions come up, feel free to either interrupt me or just save them till the end. And then I'll happy to answer them either way, if you can help me out with that. Thank you. All right. So we're going to talk WhatTheF. Hopefully this will be a fun talk. Hopefully it's going to be something new that people haven't really seen or got the chance to use yet. Probably the least important slide out of this entire deck. I gave this talk with Joe before, but today it's just me. My name is Chris Truncer. I'm just some random offset guy at FortyNorth Security. Worked on different tools that I like to code until basically stuff doesn't break anymore. That's usually when I'm happy with it. And started off as a sysadmin and did that for a lot of years until I always knew I wanted to get in security, but I wanted to learn how to build stuff first. So that's really where I started. And then after that, kind of moved into the offensive side since then. So yeah, that's all I want to say really about this. Story time. So in December of 2019, I think it was, oh God, what year is it with COVID? A client asked us to do an internal penetration test. And basically, it was basically like an assume breach. They had provided us a VM on their network, and they wanted us to have or try to accomplish a couple different objectives. One of these objectives was pretty simple. They just wanted to know, hey, can we establish command and control, right? Like that's what they want to know, if we can even get that up at all. 3 days in, we were struggling. We had quite an issue. They had really locked down pretty much all of their workstations. Everything that they had, it was basically application whitelisting was deployed everywhere. If it wasn't allowed, if it wasn't trusted, it was blocked. They had Bit9 and Carbon Black, CB response. Windows Defender ATP was deployed. So they had telemetry, as much telemetry as I've ever seen inside an environment, which was awesome, and it made it fun to try to go against like a hardened environment like this. But as you could probably imagine, it was a little frustrating because day 3, we couldn't even establish outbound comms. We had tried using various application whitelisting bypasses. So, I mean, this includes some of the basic stuff like you see like mshta, command.exe, like we kind of assumed those hopefully should be blocked. But MS Build, Wimic, Install Util, Microsoft Workflow Compiler. They did have Teams, but we couldn't get that update binary to run extra code for us. It was just a very locked down environment. So we tried, again, like pretty much everything that you see on this list, just multiple variations of all of them as well. Even Reg SVR32 and a couple different ways of invoking that. Everything was just outright blocked. And we thought we'd get an initial beacon at some point during all of this testing, but we couldn't. And so I was really impressed because these guys had locked down almost all the different vectors that we use to get either initial access or what we try to use for lateral movement inside an environment. Because we like to leverage a lot of bypasses for performing our lateral movement testing. So at this point, we were getting kind of stuck. It was hard, which was great. We didn't know what exactly to do, what to leverage. And so we started trying to dig into just various other research out there that we may have glanced over before, or just trying to find anything new. And we remembered that this article came out, and this was by Zach Brown and Shane Welcher. And it was their talk about like detecting attacks leveraging the .NET framework. And so this was kind of interesting because the authors inside of it were talking about obviously using C#, and that's what everyone really uses. And that's what everyone usually thinks about when we're talking about .NET or C# based attacks, right? However, they also talked about leveraging F#. And I knew it was a language, obviously, but up until this point in time, we really had never used it at all ourselves. I rarely see it used or discussed in the offensive community or offensive security community. This is really one of the first posts that I'd seen, even from the defensive side. There's not just a whole lot out there about leveraging that because I think personally, I think C# is a little bit nicer. I like, if I'm coding in a .NET language, I'd like to use C#. But we're like, hey, you know what? This maybe could be interesting. Maybe it's worth checking out. And so in particular, we saw this slide. And so what's happening right here is it's opening an interactive, basically, prompt for F#. So like Python, right? You type Python or Python 3 and you get an interactive command prompt. And you can just run commands at ease or however, whatever you want to do. It's just an interactive prompt. You can also run them as scripts. Same here with F#, where we could start the F# interactive version of it, and we can basically code out whatever we want our code to do and let it run. So like in this case, what's happening here is this was an example from the blog post, and it's actually running sharpsploits, one of the functionality of the get host name. So in this case, we're just seeing it's just returning a value of the host name that it's currently on, but we are able to accomplish that in F#. So that's got us what made us really start trying to figure out, okay, is this language usable? Can we possibly use this in the environment we're operating in? But first, before we can even start doing that, what is it really? How does F# work? How can we interact with it? How can we write code that helps us do stuff with F#? So we wanted to figure that out. F#, this is a lot. Some of this is straight from Microsoft. Is a very function-oriented language. So that's it's everything around functional design. It's designed, and this was interesting, to automatically infer data types. So if you're used to coding in C# where we're having to define a string or an endpoint or whatever type of data type that we are going to be assigning to a variable, you don't have to do that with F#. That's basically left up to the interpreter or the compiler, and we'll try to automatically infer what it is you're going to use, and you don't have to define it at all. The nice thing about this too is you can use pure .NET code mixed in with F#. So we can use something like console.writeLine, and we can output whatever we want to the console. But in my mind, it's kind of a pain in the ass. It's still not necessarily intuitive for me to pick up and code in, and I'm by absolutely in no way a developer, but I come from coding in Python, some PowerShell, and C#, and those at least maybe make more sense to me. I really have to think about the syntax and what I'm doing in F# if I'm going to be leveraging F#. So there's some pros and cons associated with it. The other thing is compiling binaries can be confusing if you're trying to write your code in F#. Especially if you're trying to use Visual Studio, because Visual Studio makes me mad on a whole wide range of issues. But I really like how Visual Studio, if you're trying to compile with F#, has a checkbox for if you want to build a single executable, but then it outputs 10 different files, which are all required, and it's not a single executable. So I don't think it works that way. So I just kind of hinted towards it, well, great. So how do we interact with F#? Well, we saw a couple slides back that we can interact with F# interactively and just issue our commands to the prompt and then have it run. Well, we can also compile code with F#, right? So there's a couple different ways that we can do this, which makes it nice. We can use Mono right within Linux. You can use Visual Studio. I probably necessarily that wouldn't be my first choice. You can use FSC, which is basically your F# compiler, and there's a couple other options out there. So let's look at some of the options that we explored, and we'll try to figure out what benefits there are and what drawbacks there may be. So here is a very basic F# script. Basically, we are defining like our main function. We're going to print out to the screen hello world from, and then we are have a variable here. And so this is basically just going to say whatever our first argument is, just include that within the string and then print that out to disk or to the console. And so in this case, we're obviously using like this print function. We're not using console.writeLine, but that's okay because this works. And then we're setting a return code. And so we also are doing that. So we have like our try, instead of try catch, try with, and we are sending, like in this case, like a failure code. And so what I'm doing now is within Mono, we can have F#C, and then we're providing hello.fs, which is just this script. And I'm giving it this -- standalone flag. And when I do that, it'll actually go ahead and create a standalone binary, and all the dependencies that are needed will be wrapped up inside of it. And so right when I go, I basically can copy this over to a Windows system. I have hello right here, run it with FortyNorth, and we can see it says hello world from FortyNorth. So great. We can actually use this to compile code and have it run on a Windows system. So like I said, FSC is the F# compiler for Windows. Again, it can also be run in Mono. It is not installed by default on Windows systems. So you generally are not going to be hopping on a system and trying to perform like a living off the land sort of attack, because F#, unless you're on a developer system and you got lucky, is probably not going to be installed on there. So the easiest way to get this installed for your testing locally, Visual Studio 2019, if you use that, that'll install basically everything that you would need or want in order to interact with F#. Now, finding the location of it is a whole separate story, because it can be in a couple different locations, and we'll walk through showing you exactly where it could be in just a second, or I will. Great. So going back to kind of the story I was discussing earlier is we failed to establish any sort of command and control previously when we were trying to perform any of the bypasses that we had discussed. It just wasn't working. So that was true up until we started looking into utilizing F#. And what we found was Vincent actually, this is probably like the only repo that I had seen prior to us looking to this. And even still, this is like really one of the few other repositories that I've seen out there of someone actually looking into weaponizing F#. And so since we wanted to try to figure out how to weaponize this, one of the first things we did is obviously search for some sort of like shellcode injection template that someone else wrote. And Vincent thankfully had created this. So we were able to take this code and test it out. But we wanted to figure out how can we make this work on the system that we're targeting. So let's walk through this. So again, what you see here is we're searching for F#, but F# is not installed. Like we're on all of C, when we search for it, it's not there by default. So if Visual Studio isn't installed, then it's very unlikely that you're going to see it in or already installed and available to use on the system that you're trying to target. So on our VM though that we have, we did have or installed Visual Studio 2019, and in this case, in this long directory right here, 2019 community blah 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 blah, at this whole path, we eventually see that hey, FSC is installed. And there are a couple other files that are here. In addition, here's FSI. So we have the compiler basically and the interactive application, which lets us interactively run our code. There is an alternative location. If you've installed like .NET Core, you can find at this path, C program files, .NET SDK 5.0 and F#. You'll basically find the same exact files within it. So we have FSC and FSI. If you're lucky, look for one, look for the other, because maybe for some reason it's installed in the environment that you're in. And if that's the case, then awesome. So we wanted to use FSI because we wanted to figure out, okay, how can we get our code to, our script to run without having to compile it? this took a couple different iterations, right? Because when we tried, basically what we did is we copied FSI over onto the system that we were targeting, tried to run it, and we started getting just, hey, could not load this because we're missing this fsharp.core. Well, okay, let's copy over fsharp.core. And hey, what do you know? We are now getting another error, this fsharp.compiler.private. Basically, after trial and error, we figured out that there was a combination of these 5 DLLs that needed to be included whenever we wanted to copy this over to get it to run on a remote system that doesn't natively have this installed. But once we were able to basically zip these files up, copy them over to that remote system, we could then run fsi.exe, and now we had a command prompt. So as a proof of concept script, then we basically leveraged that shellcode injection script that Vincent had built out. We added basically the ability to pop shellcode or pop calc via shellcode, and this worked. And that was awesome because we were, in this case, in the environment that we were testing, actually able to get this to run. So what we then did is we swapped that out with some beacon loading code, basically got it up and running, executed it, and we were able to get beacon to run on the system. Now the question is probably like, why was that allowed to run? Well, everything that we see here that we're using is signed by Microsoft. So these are all trusted binaries that were allowed to run in the environment. The environment that we had tested had really locked down, again, looking at abusable known binaries or known abusable binaries, such as, again, install util, MS build, and any modification that you can make to them. But FSI was not one of those that was targeted. And so because of that, we were able to leverage that and use that to get code up and running and establish our command and control within the environment we were operating in. So let's now talk about execute assembly and F#. So a very commonly used technique in modern like C2 capabilities are like the ability to execute code in basically all in memory and have it run. Ideally, if we can run like .NET applications, right? Like that's what everyone thinks of right now with like Cobalt Strike. If we use execute assembly, then it can run our .NET code in like a child process, and it will make it work without having to drop our .NET or C# application to disk. Well, let's look a little bit closer at how this works with C#. So this is our typical like hello world application in C#, right? Like this super basic. We just basically have this static main or this main method that is just calling hello world. And if we compile that and then run that within Beacon with execute assembly, it basically sets it up to run, and hey, we're actually getting hello world output, which is awesome, right? Because this is all executed in memory. We didn't have to drop anything to disk, and our code is executing. So as you can imagine, any C# code that you write should be able to execute. So you're not limited to just printing out hello world. You can have shellcode routines or shellcode injection routines. You can have like host enumeration routines, like whatever it is, or domain enumeration, whatever it is you want to do. So this is already known though, like this isn't new. Well, so how does this work? Well, so what's happening is we're having unmanaged code run the CLR, which is the common language runtime, within that unmanaged process to execute our .NET code. And basically, after the CLR is loaded within our current process, we can now execute managed code. So this is useful because we can, again, inject our .NET assembly, like C# code, into another process without ever having to drop it to disk and get it executing. And this is nice because it can help avoid AV detection. It can also help avoid like endpoint protection, copying our binary off for future analysis. There's a lot of different EDR software out there that like the second you drop something to disk, if it's not something it's seen before, it's shipping it off for review. So we can try to avoid some of these things that are performed to try to keep our tools and ensure their longevity. So this is ultimately what's happening like under the hood. I kind of have this up here largely for reference. So we're going to talk about and showing some code in just a second. But right here, it's basically like a C version of this. So we are basically calling the 4.0 version of the CLR runtime. We are, in this case, now telling it to start the CLR, and we're going to have it execute, in this case, just this application that is on disk. But we obviously don't have to have that. We can do this all in memory. But this is just a super basic implementation so that you all can kind of just see what this code looks like. So going back to like this execute assembly concept, there's really only one requirement if we're going to code an application or a utility or a script or whatever it is to run within this execute assembly functionality. And it's that we need to basically make a global try except for your .NET code. I'm sure anyone out there that's used Cobalt Strike before and have used execute assembly and have tried using it with like custom developed applications that you wrote, you're probably familiar with this invoke _3 error. Like that's super annoying, and it's always something that you're trying to figure out. Like it's a try catch issue somewhere, and you just got to find like where are you missing it. And we learned it during this project. Like that is not just a nuance of Cobalt Strike, right? Like that's not just an annoyance of that. It's required in order for us to get our assembly loaded into an unmanaged process. So everything that's being done under the hood that's where that requirement lies. It's not just like an extra check that Cobalt Strike has added in. And guess what? Well, that same issue, annoyance, requirement, whatever you want to call it, exists when we're trying to load F# code, right? Well, let's not get too far ahead yet. Like we'll talk about that in just a second. So now that we hopefully have a little bit better understanding of how execute assembly works under the hood, and again, remember that's just an unmanaged process. It's loading the CLR, which is what allows it to run a managed code within it. Let's discuss trying to apply this to F#. So the CLR can execute C# code, right? Execute assembly loads the CLR. With that process, or with that thought, like shouldn't execute assembly be able to run F# code because it's ultimately just .NET running underneath? Well, let's test this out. Here's just another super basic F# script. In this case, we don't even take it in argument. We're just trying to print hello world to the screen or to the console. We have a return value of 0, and that's all that we're doing. So it's super basic, 4-line script. So we compile that, try to run that with execute assembly. Well, we're getting invoke 3 on entry point failed. So that kind of makes some sense, right? Because we couldn't really get this to work. We aren't doing any sort of try catch. So we thought, okay, that makes sense. Maybe that's something that we need to add in. Well, what we found is that it still is relying on having this f#.core DLL run. So what do I mean by that? When we're using Cobalt Strike and we have our spawn2 process, that is the child process that your post-exploitation jobs are going to run out of, right? So whenever you run PowerPick, if you're running Mimikatz, if you're running execute assembly, that is the process that's going to be spawned, and then your post-exploitation capability goes inside of it and it's executed. Well, what we found out is that unlike our C# assembly, the F# assembly still does rely on having this f#.core DLL accessible, even if we've compiled it as a standalone binary. And because it's trying to load it, let's just say we're trying to spawn from Notepad, which is a great post-exploitation process. Just a little bit of sarcasm. That's going to be out of C Windows System 32, I believe it should be. And if we try to spawn Notepad, inject this F# capability into it, it's going to look for f#.core.dll within that C Windows System 32 because it's going to try to load it from there. And if it can't find it, it's going to fail. And we're going to see something like this. And so the reason we're getting this error is because we aren't try catching it, But if we were try catching that error, we would basically see this is that we still don't have our fsharp.core.dll accessible, which is the dependency for this fsharp code to run. So at this point, we're trying to figure out like, okay, what's the next steps, right? Like, how can we try to make sure that we have all the DLLs that we need in order to make this run? So we had a couple of different ideas that we wanted to discuss. Again, it's going to be like straight up large standalone F# assemblies, dropping into disk, and all of these ideas. And let's walk through them and see what can work. So straight standalone F# assemblies can work, kind of. Remember, if we use FSC specifically and we provided the standalone flag, this should require or basically combine all of the requirements within our assembly that it needs in order to run. So it's all self-contained, which is great. No local admin requirements are needed. We can just upload this somewhere and run it. The problem is this is a large file. So as you can see here, it's basically what 1.5, 1.4-ish megs. That's not something that we can run with execute assembly when it's all just self-contained. So that stinks because we can't run that all in memory now. And so now we're stuck with having to basically do something like this where we drop our executable on disk and have it running at that point in time. Which again, if it's not like most EDRs right now aren't really looking at this, excuse me. So they may not see this at the point, but that's not going to last forever, right? Like we don't, it's just bad tradecraft. If we can avoid dropping a disk, we're going to. So what are other options that we can do? Well, we can drop fsharp.core.dll to disk. What we need to do though is we need to drop that into the directory where your spawn2 process lives. So remember, like if we're spawning or injecting into like Notepad and that's in C Windows System 32, then we need to drop fsharp.core.dll into C Windows System 32. This is great because this works. We're only dropping like a signed binary that's trusted. fsharp.core.dll is not malicious. It's not inherently malicious. It's just a language library that's loaded in order to get it to run. The problem is that this is almost going to always require local admin rights. If we're dropping in a System 32, we're going to have admin rights in order to do that. Now that's okay because, I mean, if we have those permissions, then we can, again, run our F# compiled code with execute assembly, and that will work. Like you see right here, we have our hello world output because that DLL was dropped into that location where our spawn2 process lives. So it's great, but again, the requirement is going to be local admin rights. Unless your spawn2 value you're finding on the system is in a user writable area, then you can drop the DLL in that location, does not require admin rights, and then you can now get all in memory F# code executing. What's potentially a better option? Well, if we have admin rights, why not just add this DLL to the global assembly cache? And so what we're doing here is we're showing, we're calling gacutil, and we're basically going to be importing this fsharp.core.dll, and it's going to add it to the global assembly cache. And so this is actually going to then be located like at this path on disk, C Windows, Microsoft.NET, assembly, GAC, MSIL, and blah, blah, and so forth. And we can see there's our DLL. So this does require administrative rights. You cannot do this without having admin rights. However, the nice thing about this is if we're already trying to do this, we already have admin rights, right? So why not just use the GAC? Because if we can do this and get the DLL installed in the GAC, then at that point, we can run F# assemblies from anywhere on the host. So if we change like our spawn2 process, whatever process we're injecting our post-exploitation capability into, and it's in a completely different location, that's okay, because this assembly will, or this DLL will automatically be resolved in regardless of where we're executing our code from. And therefore, we don't have to worry about having to change or copy the DLL to a different directory. So this is nice. You can totally do this if you want to. Again, tradecraft wise, like we're dropping stuff to disk, we're adding this to the GAC. It's a trusted binary though, but how often is F# used on workstations that aren't developers is probably pretty minimal. So there's absolutely like hunting opportunities out there for this to be caught and targeted, but it's also a way for you to get your code executing if you have no other options. So at that point, you'd obviously have to like weigh your choices, pick your poison, what you want to do. So ultimately, though, is our goal was we wanted to figure out a way, how can we run an F# assembly via execute assembly without needing to drop, without needing local admin and without having to drop anything to disk. And after a couple different hours of experimenting, we finally came across a post from Jean Mays, which gave us the answer, which is using app domain assembly resolve. So before we talk about this, like, what question are we trying to answer? Remember, the question we are trying to answer is how can we execute F# managed code within unmanaged code? So we started to try to look into different loaders that exist right now for basically executing C# code within unmanaged code. So it's written in C, C++. And we found a project that was a great base for us to start with, and it's this hosting CLR project. So hosting CLR is just a C++ project that's used to run .NET assembly, C# .NET assemblies from within itself, right? So what we were curious is we want to know, hey, if we can we just give this project like an F# assembly and just run it? Like, will it just work? That would be great, right? Because we know how to compile F# assemblies. We can make a simple hello world script in F# as proof of concept, compile it with FSC, and make a standalone binary. What we then did is we took the hello world application that was written in F#, converted it into a byte array, and then embed that byte array within the hosting CLR application. And we crossed our fingers and we ran it. And unfortunately, like as everyone could imagine, it didn't work right away, right? It actually resulted in a lot of different errors, some which we could pretty easily resolve. Like we had to change the size of different constants, updating like different definitions of variables within the code. But then we were still running into this like invoke3 error with the Windows error code. And we were struggling with it, trying to figure it out. And I just happened to Google and look for that within the GitHub GitHub repo of the hosting CLR application. And we got really lucky because this was exactly the error that we were getting. And basically, someone else was having this error. And this was exactly what was right now you would still find within the hosting CLR repo. So come to find out, another individual had exactly the same error as us. So they were probably trying to do the same thing, what we were trying to do. Not only that, though, but there was a response from the original developer with code that fixed that issue. Like, how often does that happen, right? Like, pretty much never. We got pretty lucky. And the reason why we were actually, we determined later on why we were running into this error was because remember how we showed early on a hello world script that took an argument as a parameter, and it would basically say hello world from, and then whatever that parameter was. Well, our code likely would have worked if we weren't interacting or were using any command line parameters and passing them into the script, or the code. But because we are, and because we were, that's where our code, the underlying code that loaded everything, had to be changed a little bit so that I could work with it. So now we thought, great, again, we have the fix added in. Let's try to now re-embed this F# application which accepts an argument and run it within the hosting CLR code base. And what do you know? We're still getting an error message. In this case, we've got this invoke3 error. So we're still getting errors with our code, right? But that makes sense because we don't have the f#.core.dll embedded within the application. It's not in the system's path. We don't have it in the same directory. It's not in the GAC, right? So what options do we have at this point to try to help resolve this library dependency? Well, why not try what we're currently doing and embed the fsharp.core.dll within the current project? And that's where this concept of app domain assembly resolve comes into play. And so this is basically the blog post where we learned about what we can use. And just to speak to it real quickly, like another method of getting around the normal behavior of .NET assemblies and the way they search for assemblies is by using this app domain .assembly resolve method. When the assembly resolve method is called, that is called when it is unable to locate a referenced assembly, and we can basically use that function callback to have it provide the assembly that we wanted to load, and then have that be like our fsharp.core.dll or a different library, obviously. So here's just an example of this. We're actually basically overriding, we're showing our assembly resolver right here. And what we're going to do is we are basically telling it to load the assembly that we are going to provide it. I believe we're going to call it fsharp core. I'm trying to see if I have that just right in here. I wish I had a control. Oh, right here. So what we're basically going to be doing is we're going to be copying fsharp core, which is a byte array that we took and then have it loaded by this application. So remember how we discussed earlier that if we wanted to embed our fsharp application into this hosting CLR application, we had to convert that to a byte array, right? Because that's how it was going to be loaded. Same concept with the fsharp core DLL. What we want to do is then we just took that and converted that into a byte array so that we can leverage this app domain assembly resolve functionality and have it load this byte array and then resolve that dependency that it needs. So basically at this point, what we did is we did exactly this. We converted this to an assembly, or excuse me, to a byte array, added that to our disk, and then tried to run it. And when we did this, we embedded that within the application. We are then calling hosting CLR, passing it two different parameters, and hey, we actually got our code executing now right here. We don't have any errors that are popping up purely because we are able to embed that library dependency within our code, and it's able to resolve that. And all this code is publicly available, so it'll be available for you all to look at. So with that said, let's just talk about some different use cases of F#, right? So we can, basically anything that you can and would want to do in C#, you can also do in F#. So like process injection is something that is useful to us for a variety of reasons. F# does require a unique format for byte arrays, like of course it does, right? And it's not like C#, where of course it also wants to be something different. It is basically this byte format with this 0x, your byte in hex, so like whatever your 2 bytes would be, and then you add a U, Y, semicolon. So our code looks like this. And so our byte array format looks like this. I have no idea as to why like it's doing that. It's just a stupid nuance of F#. Like if they have a way to like make it uglier to look at and read, this is apparently they're choosing to do it. So, but yeah, this is what your shellcode would look like if you're trying to embed that within an F# script. So if we wanted to use pinvoke like with C#, like in this case, you want to pop up a message box, our code is going to look like this. We're just defining our message box right here, the different parameters it's going to take, and then here's where we're invoking it within our code right here. With F#, it looks somewhat similar, but just a little different. We're still defining our message box right here. The parameters, or excuse me, the data types that's going to be expecting are a little bit different. So for example, this is an pointer that I was expecting for the first parameter for message box. It's a native int in here in F#. Still have strings and like uint32, unsigned integer like 32 available right here. So basically at this point, we would just pass into the message box, whatever our code would be. And that's all that we would need to do for a message box in F#. So Vincent used shellcode injection script looks like this. This is just the F# code where we're calling virtual alloc to allocate memory within the current process. We're going to call create thread to create a thread in the current process that runs our shellcode. And then wait for single object is where we're going to say, hey, don't close that process out basically until our thread is done running. So here we're defining those API calls. And here where we are defining a couple different variables. And here's where we would put like our shellcode. And at that point, we're just calling virtual alloc. And here we can see that call. We are copying our shellcode into the location of memory that was allocated by virtual alloc. Create thread is creating a thread to run at that address, and then wait for single object is basically just saying, hey, we're going to sit here and wait. Similar concept with create remote thread. So in this case, we are now allocating into a remote process, and we are injecting our shellcode into that remote process, and also like changing the memory permissions. So these are what like our API calls look like. Here's the various structures that are being required in order to use them within our code. And then here is the actual calls themselves. So we're calling a process, we're creating a process utility-man. We are allocating space, we're writing our shellcode into that space, changing the memory permissions to be read, write, execute, read, execute, and then using create remote thread to call our shellcode. These are just super basic examples. Obviously, these may get caught, like any other language, just sort of 100% get caught. Like if we did C#, C++, anything like that, because these are just a known series of API calls that are heavily monitored and are going to be really inspected to try to determine if you think it's malicious. Because we're using F#, a lot of times just changing the language that your code is written in can at times help you to bypass antivirus or detection from EDR. So it's possible that this would be allow you to bypass it. Otherwise, our recommendation would obviously be to maybe use something like QUser APC, maybe use various other shellcode allocation and injection routines. So let's talk about WhatTheF. So we have a couple, this is basically designed to be various F# code templates or F# like repository, if you will, of different things that you can use with to leverage F#. So we have a couple different shellcode injection routines. Like we have, for instance, virtual alloc, copy, create thread, wait for single object routine. We also have the remote shellcode injection that I had talked about, or that we just looked at. We also have QUser APC, which is just, again, another way that we can get code, shellcode injected and running on a system. You can do all the same stuff that you can do with C#, you can do with F#, right? So AMSI is going to potentially still be an issue. ETW is still going to potentially be an issue. So there's multiple different websites out there that document how you can bypass it, right? You have like AMSI fail, you have, blog or GitHub repos about like just bypassing it. So you can utilize those or any other technique that you have internally to bypass AMSI and ETW within F#. I highly recommend diving into this topic and adding those capabilities into your code, because that will help your code avoid as much inspection or possibly being detected as possible. Guides to like executing F# on systems that you're targeting. If you can, like we have these different guides on how to actually do it. FSI scripting is nice because it's not a compiled binary that you're dropping. Like you can just type your commands one after another, and it's going to be a lot harder to detect than if you drop a standalone or compiled F# assembly. But we also have just other guides on, hey, whatever path you want to take, this is how you would set this up to if you're going standalone F# assemblies, or if you're using adding F# core to the GAC. We'll tell you exactly step-by-step how to do it. So what's next? So we did release, and in the repo, it does have our CLR loading application, which basically loads F#. Sorry, my dog is going crazy over here. Stop, buddy. You're okay. Basically, the unmanaged code to load the CLR and get F# executing in memory, that application is in that repo. So right now, you can use that. It does have the fsharp.core.dll already embedded inside of it. We specifically chose the version that was, hey, it's okay. We chose the version that was under an open source license. There is one on that Microsoft is like in charge of now, and theoretically still should be open sourced, but we chose the repo that explicitly stated it was, so to avoid any licensing issues. Other things that would be interesting though is porting some of your F# or your code injection routines to use syscalls in F#. We want to port other C# tooling that we have into F#, and we want to also just basically convert our execute assembly code that we have right now into a beacon object file so that we can avoid basically having any issues with spawning like a child process. So what are some limitations of this, of F#? Well, I like coding in Visual Studio when I'm using anything .NET. The compilation in F# with Visual Studio is not pretty. You can use IntelliSense with it, which does help, but you can't compile it. Like, there's just no way to do a standalone executable through Visual Studio. Even though Stack Overflow, which is the gods of all programming, says that you can, and they show the same check mark box. When you click that, you're still not getting a standalone executable. And if anyone can prove me wrong, I would love to know. I'd love to see you do that so that I can just code everything in Visual Studio. So please prove me wrong there. Otherwise, what happens if you're using Visual Studio, like you have like a binary that's outputted, but it has to have like this additional library, which will help get everything up and running. So it's not going to be all in self-contained. Additionally, when you do use self-contained binaries, they can be larger than like 1.5 megs. So you're going to potentially run into some size restrictions. Let's talk detecting F# tradecraft. Well, I'd like to thank Matt Graber and Red Canary because they reviewed all this code and like these slides ahead of time. And Matt was able to provide some detection opportunities. So we wanted to make sure to call these out. What Matt had said is like AMSI is able to catch and review the full contents of an embedded F# application. So make sure you leverage AMSI in that even if there is a bypass, like it's still good practice to have it in place, right? And if you can, try to capture that data and see what's happening inside your code. ETW can capture loading the embedded F# executable and the F# core DLL. You can also observe the CLR and MS core being loaded into the process. But ultimately, he had suggested that detection really should focus on like the behaviors related to .NET execution and like what it's doing versus like the implementation of getting code running. So not necessarily on just an F# nuance. But .NET and AMSI optics can provide like a ton of opportunities to detect in-memory loading. So last slide, key takeaways is we really just wanted to be able to present like F# as an alternative to C# in offensive tooling. F# can be executed in the same manner as C# within an unmanaged process. I think it can and should be used as a language for coding tools from an offensive perspective because there's not as much out there to help like detect it from an offensive perspective. From a defensive perspective, that's a challenge. Like, start looking into this because some attackers are doing this beyond like us and Vincent. So this should be on your radar for something that you want to start looking into to try to fill out what optics can you get, what telemetry can you see. Defenders really should instrument their fleet to try to obtain as much telemetry as possible for detection purposes, especially when it comes to looking at like the actions that these scripts are taking. Again, not necessarily just nuances or like signatures of individual tools. And again, finally, like spending time on understanding those behaviors rather than just those nuances. And that is it. That is the talk on F#. I can't see, I'm trying to see if I can load up questions, but if you have, or Corey, if there are any questions, can you just let me know?
Yeah, I did see one question go by. So do the F# assemblies, are they able to be loaded through PowerShell the same way like a C# assembly would be loaded?
So I've not tested that. That's a great question. As long as you have like the required DLLs that are needed, so like either on disk in the directory that you're operating out of, or in like the GAC, I would think that that should not be a problem. I think that should work.
Okay.
Yeah.
Let me see. I don't think I saw any other questions coming through, but man, that was an awesome talk. It was interesting.
Thanks, man. Appreciate that. Yeah, I'll be monitoring Discord. If anyone has any questions, like obviously sometimes it takes time to ingest. So I'm happy to help answer questions at any point. So feel free to reach out.